This looks like an ordinary rocket engine test, but inside that chamber, the explosion is not sitting still. A supersonic detonation wave is running laps around a ring, over and over, thousands of times every second. That sounds like the last thing an engineer would want. In this engine, it is the entire point. NASA calls it a rotating detonation rocket engine, or RDRE. The idea has existed since the 1960s, but manufacturing technology has only recently made a full-scale version practical. If engineers can control it, this looping explosion could make some rocket engines shorter, lighter, and more efficient. To understand why, start with a normal rocket. Fuel and oxidizer enter a chamber, mix, and burn. The flame moves through that mixture at subsonic speed. Engineers call that deflagration. Pumps must deliver propellant at high pressure. The chamber maintains a roughly steady burn, and hot gas expands through the nozzle to create thrust. A detonation is different. The chemical reaction is coupled to a shock wave. It moves faster than sound and sharply raises pressure as it consumes the mixture. Letting that wave run straight down a tube would end the event almost immediately. So the rotating engine bends the tube into a narrow ring. Propellant enters along the axis. The detonation wave races around the annular channel, burns the mixture in front of it, and leaves hot exhaust behind. The clever part is what happens after the wave passes. Fresh propellant starts filling that section of the ring again. By the time the wave completes another lap, there is a new mixture waiting. The chamber resets itself without mechanical valves, allowing the detonation to keep rotating. You cannot see that wave in this wide test stand footage. It is moving inside the metal chamber far too quickly. The blue-white plume is the combined exhaust from an enormous number of those laps. Why go to this trouble? In a conventional combustor, burning the propellant generally costs some total pressure. A rotating detonation engine is designed around pressure gain combustion. The detonation raises pressure during the reaction, so the engine may produce more thrust from the same supply pressure and throat area. That opens several possible savings. The feed system may not need to work as hard. A spacecraft may carry less engine mass or gain more performance from the same propellant. And because the reaction finishes so quickly, NASA research says the combustion chamber can be dramatically shorter than a comparable constant pressure design. But this is not a free upgrade. The pressure is violently unsteady. Injectors must deliver a clean mixture while a shock wave repeatedly sweeps past them. NASA testing found substantially higher heat flux than in traditional liquid rocket engines at comparable conditions. The walls, cooling passages, injector, and nozzle must all survive an environment that is both hotter and more complex. That is where 3D printing matters. NASA has built these chambers from high-temperature copper and superalloy materials with internal features that would be extremely difficult to manufacture conventionally. Additive manufacturing does not solve the physics, but it makes the required geometry and cooling hardware possible. The progress is now measurable. NASA's first Marshall hot fire campaign in 2022 produced more than 4,000 pounds of thrust for nearly a minute. In 2023, the full-scale engine in this footage ran for 251 seconds and exceeded 5,800 pounds of thrust. Then, NASA moved from a combustor experiment toward an integrated system. In September 2025, the En-ROADS thrust chamber assembly fired for just over 340 seconds. That system uses liquid methane and liquid oxygen. The larger target is a pump-fed engine in the 10,000-pound force class aimed at planetary landers in deep space missions. The technology is still being proven. A long ground firing is not the same as a flight-ready engine. NASA says the path includes a vacuum test, followed by transferring the technology to industry for specific missions. So the hidden mechanism in this footage is not simply a hotter flame. It is a shock wave being persuaded to return to the same place, find fresh propellant, and do useful work again. If engineers can keep that loop stable, cool, and controllable, the explosion that looks most dangerous may become the reason a future engine needs less mass to go farther. Real footage, hidden mechanisms, clear answers. Subscribe to Why It Spiked for the next one.